Hello, everyone. I am Simon Stewart. It is a real pleasure and an honor to be here today, particularly since this is the 15th anniversary of her stuff. Thank you very much for inviting me. Thank you all very much for being here. I hope you've enjoyed this conference as much as I have. Let's get started. I am a software engineer at a company called Block in Europe. They're best known for Square, which are the point-of-sale terminals you might have seen in cafes and restaurants. They are an excellent company to work for. I highly recommend it. The job that I do there is I work in developer experience. I work on builds and making the developer experience as good as possible. Before that, however, I used to be an SET, a software engineer in test, and I am fascinated by the intersection of these two worlds. And the intersection of these two worlds is continuous integration. We all have to do this. This is sort of a fundamental part of what we're going to do. So in this talk, we're going to talk about CI. We're going to talk about CI an awful lot, so continuous integration. And it begins with this. Good news, everybody. We're all doomed. Sorry, I was trying to sort of have a nice optimistic thing, but the world is a dark and gloomy place. Why are we all doomed? Is it current affairs? Is it anything like that? Absolutely not. It's because the AI tsunami is coming to overwhelm our test infrastructure. The industry is seeing more and more code being written by AIs, and all that code needs testing. And all those PRs that they create, those go through our testing infrastructure. And, you know, that shouldn't be a problem. But it will be. And why is that? It's because we have CI pipelines like this. This is a traditional CI pipeline. We focus on completeness with these things. Obviously, your CI pipelines are better than this, and they are more sophisticated. But this is the sort of general principle of what you do. You start by cloning the repository, and then you might sort of do linting separately, but you run the small tests. And the reason why you run the small tests is because you want the feedback as quickly as possible, and you know that everything else is going to take a long time. And then when they pass, you start running the medium tests. And maybe you start deploying the artifacts to the UAT environment. So when the medium tests pass, you're ready to start the large tests. And you run all of the large tests, and it's magnificent. And finally, you upload the artifacts. If you're practicing continuous deployment, you might then begin the continuous deployment pipeline after that. It takes a lot of resources to do this. And the problem is, as more and more PRs are coming in from AI as they're being written, our CI infrastructure will crumble. It will not be able to take the stress and the strain we're going to put it through. I mean, how many people work at a company where everyone is delighted with the speed of the CI pipelines right now? For those of you sitting on the front row, nobody raised their hands. You know, it's only going to get worse from here. But before we figure out what we can do about this, we need to answer a far more fundamental question. And that question is, why do we test? There must be a purpose for it. Well, the reason that we test, as far as I'm concerned, is we want to get a new line of code into production as quickly and cheaply and as safely as possible. If you watched Rob's keynote, you would know that the reason for that is because until the code is in production, it's just a cost. It doesn't bring us any value. It's only when it's in the hands of users that it can start generating interesting things for good people. So quick is important as code is useless until it's in production. And cheap is kind of interesting here. Like when you say cheap, you normally think of the dollar amount, like how many euros, how many florins, how expensive is it to run. But it can also refer to engineering cost. Code should be cheap in terms of engineering hours to maintain. And there's obviously a trade-off between those two. And that leads us to the next reason why we test. We actually test to manage risk. Testing isn't about perfection. Like, we all know that there is no such thing as perfect code. I have seen bugs in Hello World, which is unimaginable but possible, and I've seen it. People don't capitalize the W because it's a proper noun, and they don't put a comma in because there's a pause, and sometimes they forget a semicolon. It's awful. So we know that literally no piece of software is completely bug-free. The best we can do then is we can minimize the risk as much as possible. As an aside, we work in testing or QA orgs quite often, and I really hate that name. And the reason why I really dislike that name is because it disempowers people. If you say to somebody, I'm responsible for quality, that means they are no longer responsible for it. It is quite hard to persuade developers to write tests in the first place. It is even harder if you say, my job title has quality in it, yours doesn't. That's quite powerful. But we are in the business of risk mitigation. So I am suggesting, between you and me here, that we rename our organization's technical risk mitigation, which has the handy acronym of TRIM, which means slim and nice, and who doesn't want to be trimmer? The other advantage of doing this is that we can then start looking at other places where we can put quality into the software development lifecycle. You can go and look at people, you can say, the design you have here isn't appropriate. You can have a different level of conversation, and it's going to be great. So I am going to talk to all of you as if we were trim engineers who are responsible for the entire SDLC, and you can make informed technical choices. And to reiterate, testing is about risk, not perfection. We can never test everything, and confidence comes from risk awareness. So, we know there is going to be a deluge of new tests. We know our test infrastructure is under strain already. To survive the coming storm, we need to do more with less. And that is why our traditional CI pipelines are no longer appropriate and no longer fit for purpose. We need to do something better. In reality, it's unlikely we can't run it's likely even that we can't run every test. So I have to warn you, I know it's the end of the conference, there is a little bit of audience participation coming up, so just brace yourselves if you're a bit introverted. First question to all of you out there, if we change a README, do we need to run all the tests? No, of course we don't need to run all the tests. What a ridiculous thing to say. Fine. If we change just a single test, not any of the production code, just the test, do we need to run all the tests? Nope. We don't need to run all the tests. Should go without saying, right? Intuitively, it's believable. What if we change a core library that everything depends on? Do we need to run all the tests? I mean, maybe. If we count linting as a test, and we haven't changed any of the source code, we don't need to run the linting checks anymore, but we might need to run all the other tests. So, maybe. So, what do we do? How do we make it so we run fewer tests? Well, this is where set theory comes in. We're going to be choosing subsets by mining the build graph, which sounds very exciting, but this is where the set theory of the title of the talk comes in. This is a build graph. Each of the dots represents a component in the build. You'll see here that I have changed the file in green. Just by manual inspection of the build graph, you can tell that these are the only things that need checking. Similarly, if I change this file, I only need to change these things, test these things. And again, if I change this, I only need to check these things. Finally, if I were to remove a file from the entire repo, it's basically the same thing as making the most drastic edit you can imagine. You only need to run these things. This process of mining the build graph to identify the subset of tasks you need to run is called target determination, and it can be super quick to implement it. If you're using a tool such as Bazel, or I believe NX does this, or Turbo Repo, there are already built-in mechanisms that allow you to identify the dependencies of changes you have made, and that allows you to identify the subset of tests to run. Other tools, Gradle, Maven, NPM, take your pick, make files, you will need to do additional work, but the theory is still sound. Now, the interesting thing here is that larger repos will benefit most from target determination and test selection. And why is that? Well, the larger repos have more pain. To run all the tests in a large repo is really expensive compared to running it in a small one. Second of all, when there's more data, you can model things better, and you're more likely to run only a subset of the tests. And finally, large tests tend to contain more overlapping tests. So what you can do is you can rank those, and you can go like, these are the ones that we want to run. So when should you use target determination? Well, the first time is where CI queuing is a bottleneck in your build. Second time is when you have slow end-to-end test suites. Or you have expensive tests. You need to access things in a device farm, for example, or there's an expensive one-time setup for a UAT environment or something like that. Or when there are strict PR SLAs. So we need to get a result within 10 minutes. That's a good reason to do target determination, because you just don't have time to run everything. Great. So we used target determination. We found the ideal subset of tests to run. We're done, right? We can go home, call it a day, relax. That's right, isn't it? I kind of wish it was, but it's not. And there's a good reason for that, if the slides will advance. The reason for it is the shape of our source repositories shapes our test strategy. What on earth do I mean by that? Well, here is an idealized source repository. Green things are tests, the yellow thing is an application, the white thing are libraries. It doesn't matter. But you can see here that the components are more or less separate. They're loosely coupled, and if you were to make a change in any of the libraries, you would make it very easy to run just a subset of the tests. Target determination works brilliantly here. But we often see repos in this shape. Imagine if this yellow thing was the Android or iOS app that you're trying to test. Your end-to-end tests all depend on that application having been built. Suddenly, even the smallest change in any library is going to cause all of your end-to-end tests to run. Target determination is less useful here. We have these pinch points in our source repositories, and because of that, we have inefficiencies in our testing. Given this, how can we reduce the number of tests we need to run? We cheat. And we're going to use heuristics. That's fine. It's going to be okay. We're smart people. We can do this. Heuristics trade safety for speed. When you run every single test, you are guaranteed that if a test were to fail because of a change, it will fail. When you use heuristics to only run a subset of those tests, there is a possibility you will miss the test that should have failed. It's okay. Why is it okay? We want to get a new line of code into production as quickly, as cheaply, and as safely as possible. But we test to manage risk. We are now, as part of the technical risk mitigation team, making a conscious choice about how we're going to mitigate risk. So it's up to us how heavily we rely on heuristics. If a test failure is utterly unacceptable, you have to run every test. If it isn't, you can run more heuristics. If you don't care, don't run any tests. That's fine. By the way, I occasionally talk about an escape. An escape is a bug that would have been caught if a full test was run, but doesn't get caught. So how do we use heuristics to do this? Can we use historical builds to maybe help us pick the right test to run? Yes, we can. That's good. The approach that I'm going to describe now is one that I have seen built. You may not understand it because we're going to go into some of the technical details. Don't worry, the idea here is something you should take away and you can apply in your own places, and you can talk to engineers if you need help implementing it. But I think it's pretty clear. Historical coverage data informs our test selection. Well, what do I mean by that? Well, what we can do is we can run each test in turn against the application under test, and we can gather coverage information. We can aggregate per class or component within our application, and we can map tests to class names. So we know that when this class changed, this test, it needs to be run. When this class changed, that test needs to be run. The collected coverage data is stored in a database or some other external store as a many-to-many mapping between tests and classes. There we go. Then, when you come to run your test run again, you can query that historical data for new test runs. When a pull request is opened, you can look at this mapping, you can identify which classes have been modified from the PR, and from that you can figure out which tests have previously been useful for running this. That's great, because that allows you to take those end-to-end tests that would have been run and only run the subset that actually count. The results I have seen in the systems that have implemented this have given you, at best, about a 50% test reduction in the number of tests that need to be run, which is pretty good. It is possible that if you used additional heuristics, you might be able to get that number even higher, but 50% is one I will take. The way to keep this reliable is you need to update that coverage data to prevent escapes. If you just do it once and you never update it, your tests will slowly become more and more out of sync, and you will have more and more escapes. And also, we can combine heuristics and mining the build graph to narrow the list of tests further than we would just by simple inspection of the tests. Good. Fabulous. Well, it would be, but we are in a fashion-driven industry. I remember, because I am old, when Ruby on Rails was going to dominate the industry, nobody would ever do anything different. It would all be Ruby, and Ruby was what we were going to use. Who here is using Ruby on Rails as a daily driver? I can't see any hands, never mind. What about JavaScript? Isomorphic JavaScript was going to be what was going to save the world next. We were going to write the code, and it could either run in the browser, or it could run on the server, or it could run somewhere else, and it was going to be amazing. And JavaScript is popular. But do all of you write JavaScript? Absolutely not. But AI is a new hotness. We have had so many talks at this conference about how powerful and effective AI is, and how it's going to change the world, and it's going to be great. And they're right, it is going to change the world. It is going to be great. I think we might be in a hype cycle at the moment. I think it might be over-promising, but we can do some really interesting things with it. Can we use AI to help us do test selection? Only joking. Of course we can. And there are a couple of ways that I'm going to describe that you can use AI as part of your test selection. The first one is based on this paper that I've linked to from archive.org. And it's a paper written by Meta. They do some really interesting work with AI, and they know what they're talking about. Again, this is going to be a little bit technical, but don't worry. The nice thing is, I've asked ChatGPT, we can implement this ourselves. There are open source libraries that allow you to do many of the same steps. And again, if you've got a data engineer or an AI expert, you could probably whip something together if you needed to. So, LLMs are really good at pattern spotting, and that's what we're going to use. So the paper was about Meta's work on predictive test selection using an LLM trained on test failures. The first step of the process was they treat test selection as a sort of binary classification problem. Given a code change and a test, can we predict the probability that the test will fail? Features are extracted from both the change, like the changed file or the history of it, and the test, historical failure rates, project metadata, other bits of information, plus cross features relating the two. How do they find these cross features? They use gradient-boosted decision tree models for this. That sounds really fancy, and if you use it, you will also sound fancy and clever. Now, a gradient-boosted decision tree model, bit of a mouthful, is a smart ensemble of many small decision trees, where each one learns from the mistakes of the last, so the overall model becomes highly accurate at making predictions. That might have sounded like nonsense to you. So allow me to give you a metaphor, which is these things are like having a group of advisors, each one slightly better informed than the last, that combine their opinions to reach a confident conclusion. And we do this ourselves day to day when we're doing testing. We'll have a chat with our colleagues, go, should we worry about that? And they go, no, don't worry about that. What about this? Yeah, that looks suspicious and we should have a look at it. We do this intuitively ourselves. This is just fancy machine talk for the same thing. More jargon, calibration. What is threshold plus top K heuristics? I'm glad you asked. A top K heuristic is a rule of thumb for picking the most likely items from a ranked list. That ranked list is clearly a list of tests. They're ranked in terms of probability of being run, and we're going to select a subset of them. So to turn predicted probabilities into a concrete test subset, Meta used two mechanisms. The first is a score cutoff threshold, above which tests are selected, and two, selecting the top K highest scoring tests for each change. That is, they rank all the tests and they go like these ones. The union of the thresholded tests and the top K sets balance give you the chance of recall, that is, catching failures, and the cost, the number of tests to run. Meta claim 95% recall, 95% chance of catching a test failure, and the cost is halved in production of running all their tests, which is an extraordinary number. Now, Meta have a massive code repository. They have a load of tests. They have a lot of test data. Your mileage may differ, but the principle can be applied. They have maintained high fault detection while drastically lowering test execution effort, and they have very few escapes. You can build this if you need to. Go and read the paper, get ChatGPT to summarize it for you, and then ask ChatGPT to implement it for you, and it would be like the most circular thing you could possibly do, and it would be a lot of fun. Test flakiness, non-deterministic failures, is a major problem for the Meta approach. Training on flaky failures leads to poor models, and those poor models mean that you don't select the right tests. How do they cope with this? Well, Meta mitigate this by retrying failed tests up to 10 times during data collection. And if a test ever passes, it's labeled as flaky and excluded from the dataset. Thus, the model that's being trained is based on true failure signals, not flakiness, improving the predictive accuracy of the models they have. So, be strict about handling your flaky tests. And here we take another minor diversion. You're all now members of TRIM. If you came to the talk I gave on Tuesday at a testing meetup, you will know what I'm about to say now. I apologize to those of you who did. Your CI build must give you strong signal. Otherwise, you might as well not be running CI. If when you run a build, people look at it and go like, oh, it failed, it does that. Why were you running it? If you then have to rerun it, you've wasted time and effort. You get a delayed feedback loop. It is awful. You must have strong signal from your CI builds. So what can you do about flaky tests? I have a whole talk in this. I think it's up on YouTube as well, but I'll give you the super quick version, which is in your repos, in your code, you've got to detect flaky tests, you've got to assign them, you've got to give them to an individual. Do not give them to a team. If you give it to a team, nobody on that team will do it because they believe everyone else on that team is responsible for fixing it. You resolve it. You either take it out of your test runs, you mark it as flaky, you make sure it's no longer in CI, and then you fix it. Fixing is fine. I don't care whether the fix is deleting, somebody going in and fixing it, doing a whole bunch of extra work, doesn't matter. And you verify. Once the fix is in place, you put that test back into CI. The key thing is that once a flaky test is detected, you must remove it from your builds. Just as a matter of code hygiene, it doesn't matter whether you take anything else away from this talk, do that, you'll be fine. Right, that's the diversion out of the way. Thank you for bearing with me. And now we can talk about another way that we could use AI. So AI is really interesting, right? The state of the art keeps on moving, and this is relatively new. We could use AI as a seer. We could coordinate subagents to do things. Subagent, is anyone familiar with this concept? It's where you have a coordinating AI, and it tells other LLMs to go and do bits of work for it, in the same way that a manager will tell people in their team to go and do some work, and then they aggregate the data and they pass it forward. Same kind of concept. So the first thing that we're going to do, again, we're going to narrow the list of possible tests from a PR by mining the build graph. We're going to use target determination. That will give us a list of candidate tests. From that list of candidate tests, there are two classes that we're going to pull out. Direct tests have an immediate dependency on a change component, and they should always be run, right? If something depends on the thing, absolutely. But the transitive ones have like more than one hop, and you need to figure out where those are. And that's where AI comes in. How do we identify the transitive tests we need to run? Really important point coming up here. This is vital. AIs, LLMs today depend on this concept of a context window, which is approximately, depending on your AI, 100,000 to about 1 million tokens. And a token could be a word or a small subset of the code. But it's how AIs measure how much memory they have. Context windows are relatively small, and repos are large. So we're going to segment your repository into components. Now, this might be obvious in some repositories. If you're using Gradle, you might have a top-level project per module, and that is a fantastic component boundary. If you've got a source repository that's organized in some other way, you're going to have to do some work, but you need those components. And each component has a public contract. So that includes like APIs, but also resources, dependency injection bindings, feature flags, manifest entries, schemas, like the things that the tests and the world around it will depend on. And each PR affects different components, logically. Like if you make a change in like an order workflow, maybe the status screen is unchanged. So what we're going to do is we're going to ask a subagent per component whether a particular test modifies that component. That will give us a list of candidate tests that we can run. This is very similar, by the way, in spirit to what we did with coverage information, but now we're using LLMs, so it's significantly slower, more expensive, and ecologically damaging. But it's also very trendy, so that's good. Once we have identified the combination of direct and transitive tests, we run them. Good. So if we use test selection using one of these three methods and target determination, we'll be okay, right? We'll be ready to face the oncoming storm. Yes? No? Maybe? Let's take a step back and think about things. This is the sort of classic diagram that consultants love. There are three things, and you get to pick two. We always want speed to be nailed down. So that is one of the two that we pick. We have, so far, been playing with safety, and we don't care about cost so far. But what if we take cost instead of speed? What could we do that would change how effective we could be? Well, the obvious thing is that, like, the gating factor of how fast our builds are is how powerful our build machine is. I don't know about you. Like, my laptop has some ridiculous number of cores. I grew up where a machine had one core, it could do one thing, and now a machine can do 16 things and run very hot. Your CI machines probably can do 32, 64 things simultaneously. And that's called vertical scaling, right? We just put bigger and bigger machines and things run faster because we can do more. But if we could scale horizontally, we could go even faster. So the interesting thing here is that build graphs tend to be shallow and wide. And what do I mean by that? Well, imagine you have a C or C++ program. Each of the C files needs to be converted into an object file. And once all of the C files have been converted, they then get linked together into a single archive. But you can have hundreds of C files, and they each need to be compiled. If you've ever compiled C code, it's taken a long time. That's why. But that work is shallow and wide. It is easy to parallelize. And there are two strategies we can do in order to follow in order to do parallel execution. And the first one is sharding, and the second one is remote build execution. So in sharding, what you do is you go, I have 4 machines, and I will subset each of my tests. So this machine gets a quarter, this machine gets a quarter, this machine gets a quarter, that machine gets a fifth, because we're not good at maths. No, that machine gets a quarter. It's great, right? And then we can run it. Now, the problem is you then end up with some machines lying idle because not all tests run at exactly the same speed, take exactly the same amount of time, and require the exact same number of resources. They're all different. And so you end up needing to do manual balancing of the shards, and it's complicated. The other thing as well is you somehow need to get bits of the build onto the machines that are running the shards. You don't want to do it's just painful. So the thing that I prefer is remote execution. Now, there are build tools out there that support remote execution out of the box. The one that I like is called Bazel, B-A-Z-E-L, which is derived from an open source tool that Google have released. Another tool is Buck, which is also pretty popular. That allows you to go, I have a single machine running the test. It will talk to the 4 machines that I have who are capable of doing things. And whenever one of those is available, I will give it a test. I will give it a test. So you get better utilization of the machines that you have. Does that all make sense? I hope it does. The downside with this, test sharding is easy. Your developers can just keep on doing what they're doing. If you move to a build tool that supports remote execution, you're asking developers to change. Developers don't like change. You quite often talk to them and go like, as a person working in developer experience, they go like, what would you like? They go, I'd like everything to be a lot faster and a lot easier. And you go, can I then change something for you? They go, absolutely not. I have my workflows and they are holy and you cannot touch them. It's like, this is going to be tricky. Developers don't like change, but if you can persuade them, remote execution is fantastic. Great. So maybe we can do more. That would be good. But what else could we do? We could, if we wanted to, we could do less. That's a good idea. This will require us to be brave. As people working in test and quality, it is common for us to have less influence than we would like and that we would want to offer people. But as Trim, we should expect people to listen to us. Be brave, own the space. What are we going to do? Well, what would we do if we could change anything? If we could change anything in order to make builds faster and more scalable, what would we change? This is the problem. Our CI infrastructure will crumble because our builds do too much. Our builds tend to evolve over time. They grow, they become bigger. And typically this means that we're doing too much work in our build because we've never reassessed the decisions that we have made previously. We all know that fast feedback is a superpower. Slow builds is slow learning because you have slower iteration. Faster builds lead to better flow, fewer bugs. So what can we do to encourage fast feedback? Brace yourself, I'm going to show you something that you all know and you're all very familiar with. The test pyramid. We've seen this millions of times in our career because clearly it is the silver bullet that will make everything better. I know it's old and I know there are improvements, but the fundamental concept is great. Small tests are fantastic at providing feedback. They run really quickly, but they don't have much coverage. Like when a small test fails, you know exactly what's gone wrong, but you need millions of the things in order to get the coverage you need. A large test is simpler to write. It gives you far more coverage, and that's fantastic, but when that test fails, it doesn't tell you exactly where that failure is, and you need to spend time doing it. Clearly, there's a balance that needs to be struck. How do you strike this balance? I think what we ought to be doing is writing the smallest test that could possibly work. When you have a bug or a new feature, or you're trying to fix something, try and identify what the root cause is, and then try and wrap the smallest test around that to prove that the fix is in place. Now, that's great because a tiny, precise fix runs significantly faster than a large one. It's far more precise, and you can pinpoint where problems are. It's also important to remember here that the smallest test may not be small. You might actually need to do an integration test between 2 layers. You might, at some cases, actually need to do an end-to-end test in order to verify things. However, if you follow the process of writing the smallest possible test you can, you will naturally lean toward working with a test pyramid. That's just a consequence of always writing the smallest thing that will possibly work. They accumulate, and that's good. But writing a small test can be difficult. Code bases are not typically designed to have small tests written on them. How do you get to a world where you can actually write these things? This book by Michael Feathers, I'll stand out of the way, by Michael Feathers is old. It is an ancient tome in the world of computing, and it is one of the best books there is. His definition of legacy code is any code without a test, which I love because there's so much legacy code. But he has a strategy in there for how to find the seams within your applications and to drive down to write small tests and break apart those things. Remember, as trim, you are allowed to make architectural choices and suggest them to the team and try and drive those things forward in order to make the code base more testable. And the reason why you want it to be more testable is because you want things to be faster. The reason why you want it to be faster is because then you can get it into production more quickly. The reason why you want it to get it into production more quickly is it will make everyone's lives that little bit better. Good. We're writing small tests. What else can we do? We can delete things when it's safe. Linda gave a talk at the testing meetup where she was discussing the testing strategy that they had followed. And it was really interesting because as they shifted left, they found that the large tests they had were providing less and less value to the point where occasionally they were providing no value. When a test offers no value, it is safe to delete it, and that's exactly what you should do. Now, we can safely delete tests because we're using source control. And if we find that we need it, we can pull it back. The next thing we can do is we can mandate that AI-generated tests must be as small as possible. We can find it hard to tell our developers to do things, but AI, it has no feelings, it doesn't care. You can tell it to write the smallest possible test, and it's not going to sulk or complain to your manager, it's going to do it. The problem is that AIs are also pattern following. So if your repository is filled with large tests, when you say write a test, it will write a large test. Ugh, that's not what we want. So you might need to be a little bit coercive with it and force it to do it. But if we're using AIs to write our tests, let's use AIs to write the kind of tests that we want to run. And finally, we should review the test suites regularly. We are using AI more and more. AI doesn't do refactoring. It tends to just write more code. We see this already in the data coming out of GitHub about the explosion of sizes of code bases in their repositories as people adopt AI as coding aids. We know this is the case. As a number of tests increase, the amount of overlap between tests probably increases as well. So we can either do a manual review of test suites, or we can use AI to solve the problem that AI has caused us by getting it to review our test suites and going like, is there overlap? Can we reduce this down? And we should consolidate the tests ruthlessly. We should try and get our test suites to be as small as possible. We have covered a lot of ground in this talk, some of it technical, some of it theoretical, some of it a call to action to rename yourself to trim. But what are the takeaways? First one is that we can thrive in this coming tsunami of AI-generated PRs. We can do significantly better than we are. And even if we aren't in a world where we are going to be inundated and swamped with PRs generated by LLMs, making these changes will make life better for our developers and for us. Just remember, testing is about risk, not perfection. We can never be perfect, sadly, but we can reduce risk. And the future of testing is about running the right tests, not running every test. Test runs shouldn't be a static thing. It should be dynamic. We should pull data from the build graph, and we can use AI to help us figure out what we need to do. We can use information we have gathered from previous test runs to make these things alive and flexible and useful. I agree. So, I should have called the talk Testing as Risk Management, really. We have looked at set theory. The shape of your repository helps define your test strategy, and we can use target determination. Statistics. We can trade safety for speed with feedback loops, so we know that we haven't broken anything. We can use historical coverage data that can inform test selection. AIs. We can use them in two ways, as a pattern spotter for predictive text selection, like the Meta paper, or we can use it as a seer, reasoning about components and basically doing what we would do with coverage. And finally, we can do less. So we should be trying to focus on small tests and making the best utilization of the resources that we have available to us. And with that, I am done. Thank you all very much for your time and attention. It has been a pleasure talking to you.
And it's been a pleasure listening to you. Are you ready? We can go on with the Q&A. Okay,
Yeah, let's do this.
Can you insert bugs into the code as a test for the test choosing?
So presumably this is to figure out whether the strategies you have for doing test selection are working. Yeah, why not? Like, we should be testing the things that we write in the same way that we are testing everything else. If you want to insert a bug to verify that test selection is working, go for it. If it doesn't catch something, then that is a really useful piece of signal that you can take, and you can try and figure out, like, why did I miss that, and what do I need to change in order to improve it?
Okay. So, Simon, can you please provide some examples of how to apply top K heuristics in everyday test design / test selection?
So top K heuristics were mentioned in the AI part, and basically what you do is you take a list of things and you give them a weighting. So you stack rank them effectively, and you go, these are the things that I most want to run. If you don't want to use AI, there are other methods you could do to do test selection. Things that I would take a look at are recency of change would be good. Historical pass failure rates would be good. Something that's never passed, I wouldn't run. Something that has always passed, I would never run. You know, you can do this, but the basic principle is find a way to order the tests that you have, and then select a subset from that by picking the most relevant tests.
Okay, we've got a bilingual question here, a German-English mix. Is removing flaky tests dangerous? Guessing those can be important?
That's an excellent question. Yeah, it can be dangerous. Like, we don't write a test for fun. Do we write tests for fun? Does anyone just like, ha, I've got nothing to do today, I'm going to write a test? Good, I'm proud of you.
Me too.
However, most of the tests we do serve a purpose. That flaky test clearly meant something. Now the question is, does the value it provide be sufficient to keep it in the CI? And there's a couple of things we could do. If a flaky test is like a 5% chance of failing, we might just try and rerun it. You know, if it had a 5% failing the first time, second time it has another 5%, 5% is not much. Like, there'll be a threshold where it'll work. But you should remove these things because they're not providing signal. You can run them out of band, so you can go, oh, we've got all our flaky tests, and it may or may not provide any information. I don't think that's a useful thing to do. If the test is valuable, somebody should take the time and effort to figure out why that test is failing, fix the fundamental underlying cause, and put that test back into production. If it's not stable, it's not providing any value.
Okay, this is my favorite. Gathering coverage data. What about legacy systems? What great changes can happen, and many tests can be outdated and Fehlung for a long time because ma. Good luck. This is my absolute, because ma.
I think that's just a howl of frustration, right? Like,
yeah, maybe. I was thinking mama. Not sure. Maybe you just ran out of the options.
I've occasionally looked at tests and gone, oh, mother.
Okay, good luck.
So tests that are outdated or failing for a long time, delete them. Have that difficult conversation. If they're not providing value, you're just keeping them as pets. Like, there was a move in the DevOps community where people move from, they call it cattle, not pets. Like, we used to set up a machine that used to be carefully maintained, and we used to call it like some cute name, invariably like after a Greek or a Roman god. And we go, oh, look, we've got these 5 machines. And now we just spin up pods in Kubernetes and we pull them up and tear them down. We don't care. That's how we should feel about our tests. Currently, we lovingly craft and maintain these things, and they're not providing value, but we wrote them and we want them to be here. But they're not helping. They're actually slowing us down. They're making life worse. It's okay to delete them. They're in source control. If you need to revivify them, if you need to pull them back, you can always do that. It's always an option. But yes, so legacy systems, it can be hard to get coverage information out of that. When that happens, maybe the coverage approach isn't the one you should use, and you might want to consider one of the 2 AI approaches that I suggested.
Yeah, you're one of those speakers who I could keep up here for at least 45 more minutes. We have so many more questions, but I don't want to squeeze it into 21 seconds. So, ladies and gentlemen, Simon Stewart!
Thank you very much.
Thank you very much. You were amazing. Thank you so very much.